like I said, this has to be satisfied at every point, correct? So maybe here is another point. This will, I'll call it P1 now, here is P2. So also at P2, the same has to be true. So actually I'll call this U1, and the second neighborhood around P2, I'll call it U2. They may overlap, fine. And this U2, there has to be another phi 2, and I'll call this phi 1, that maps U to a flat space Rn, okay? So at every point you have to have this thing. And remember, if there is a phi like here, because it's diffeomorphism, its inverse maps you from this Rn, from the flat space, to the neighborhood, and the same here. Phi 2 inverse, okay? And we can have overlap. These phi's, whenever there is overlap, they have to be compatible. I will not go through this compatibility condition. We will not need it in our class to just rigorously prove that something is an atom. Although this really has some very nice geometrical meaning, well, the circle around every point, it looks like flat, or you can flatten it out. The sphere, this guy, I can take this part and make it just flat. I will refrain from these geometrical things, because although they help you visualize things, but I really want to make things abstract. So I'll give this example. We have a space of BMW cars. Okay, I want you to think of it like this. It's really very abstract. Yes, a manifold can be something very nice, surface, curved surface embedded in Euclidean space, like a circle, a sphere, a donut, or whatever. It can be a nice surface. But it also can be a very abstract object. Well, the set of BMW cars, that's fine. To prove that it's a manifold, I don't know if it's a manifold or not, I'm just giving an example. But at any point, here is a car, right? Probably this car in the 1995, so locally around the car, maybe the set of cars from 1990 to 2000. There has to be a map, mapping this guy to a Euclidean space, flat space. Bunch of numbers. So this car has to be exactly represented by a bunch of numbers. Well, probably I can represent the car by its maybe power, horsepower, dimensions. These are 3 numbers, right? Dimensions are 3 numbers. Power is 1 number, real number. And what else? Maybe weight. Let's assume that this is enough. So this is 5 real numbers. So you have to have a map that maps every car to R5. For every car, give me 5 unique 5 numbers. And these unique 5 numbers, if I give you 5 numbers, they have to completely characterize a car. Okay? Well, maybe in another period, over the, maybe now in the old era, maybe it's between 60 and 70, I have another map to 5-dimensional space. It might not be the exact same things. Probably back then the weight was not that issue to characterize cars or differentiate between cars. Probably the cost was a huge thing, so I'll replace this with cost. So cost, power, and dimensions. Over this period, if I give you the cost, power, and dimensions of any car, they should exactly characterize this car. Okay? Any questions so far about this? I want you to have it as abstract as this. I know it's not the best way to explain it. Yes? No?
The only question is, like, what do you mean by a flat surface?
Very good. Now we come to this point. But I'll explain it exactly now. Any question before that? Question about this.
Why are the variables, why can they change?
Say it again, please.
Why the variables can change?
Not necessarily, but
I mean, it's like
I'm saying you have a freedom to change the variables,
Okay,
but not necessarily.
okay.
But I'll show you that you cannot use the exact same variables for the entire thing, for sure.
Okay.
Because if you can use the exact same variables and the exact same relation, then you're saying that your surface globally looks like flat space, but it's not. Globally. Locally, yes, but globally, no. Right? Yes?
Could it map to R4?
No. This is a very good point, or at least we'll not deal with it. An n-dimensional manifold will always be mapped to an n-dimensional Euclidean space. This is a good point. Any question? Now let's know the difference between the curved space and flat space. One of the basic differences. For example, you guys take things for granted. You think that whenever I have a space, I can add things together, right? No, not necessarily. You cannot add 2 points together. I cannot add 2 cars together. Nothing. But I can add here. I mean, power and power, I can add them. Dimension, I can add them. And they are just numbers. Over there, they are not numbers. Right? I'll give you an example that is more interesting. Even on the object that we really feel, a sphere. You have a point here on the sphere, a point here on the sphere. Can you add these 2 points? Can you add these 2 points? No, I cannot add 2 points on the sphere. How can you add them? Do you think you're gonna add them from a Euclidean point of view? So this is probably 0, 1, 0 if this is x, y, and z. So this is 0, 1, 0 and this is 0, 0, 1. And I'm going to add these 2 points together. So what is the result? The result is 0, 1, 1, right? Where is 0, 1, 1? 0x, 1y, 1z. The point is here. This is the result. It's not on the sphere. You cannot add points on the sphere and get a point on the sphere. And the same here. You cannot add 2 cars to get a car. In Euclidean space, you add points and get points on the same space. It's not only that, it's much more. The addition is the very first step. You add things together, you can measure distance between points on the Euclidean space, right? You have a distance function. Give me any 2 points, delta x squared, delta y squared, delta z squared. This is the distance between the 2 points. This is not the case on a curved space. How are you going to define distance? I don't know. How are you going to define a straight line? We know a straight line in a Euclidean space. I don't know what's the straight line on a sphere, and this is what we're going to talk about in these 4 lectures. Okay? What else? I know the angle between 2 vectors. I can do dot product, right? And get cosine the angle in between. Over there, the dot product itself is not defined. Okay? Any question about that? So, a Euclidean space is the best space ever that you can deal with. Why? Because you can do these things. You can add, you can get distance, you can get angles. Okay, and this hierarchy is order. So if you can get angles, this is the finest. If you can get angles, then for sure you can get distance, for sure you can do addition, and we're going to know why later on. In Euclidean space, I can do all. In general, in any space, no, not necessarily. You cannot even add things to it. So, and here is the point. I want to do calculus on curvy space, because calculus, the very basic element in calculus is differentiation. And differentiation is simply subtracting things together, if you remember, right? Function at x plus delta t minus function at x divided by delta t, and take the limit. So we need to subtract. In other words, we need to add. So if you want to do really calculus on curvy space where addition is not even defined, then, well, hopefully you can map your space locally to a Euclidean space where I can do the calculus and come back. This is actually the main point about differential geometry. Okay? Any questions so far? Yes, you?
Just a little bit confused. So you have like 2 points and they could overlap, right? The space around it overlap. And once you overlap, it's not a one-to-one relations anymore, like one-to-one relations between. It would be mapped to another space if possible.
What do you mean? Why? So this phi is one-to-one relation.
Right. And
So let's talk about a point in the middle, this point, right, in the overlap. This point can, according to this relation, can be mapped here, this point can be mapped there, right? Actually, the compatibility condition is that this composite map, because I can go from here to there, by the way, this composite map has to be nice. So this is what I call, it cannot be any phi's, they have to be compatible with each other, but we'll not stick to that. It actually doesn't add much constraints, it's not a big concern. But you have to take care of it. Let's be more serious. Let's talk about some example. Yes, Mikhail?
Well, it's about what you say. So if Rn and Rn are the same,
They have to be.
yeah, but like in the other example, I put that there are different characteristics.
Yes, but still, this is a flat. I mean, you can always map Rn to Rn by what? You know,
Yeah, so it would
matrix,
be,
right? It's a linear space. The matrix map any point here to any point there, right?
at the end will be the same point.
Oh yeah, it has to be. This is the compatibility condition. So let's have an example. Do you need this board? Let's talk about an example. So I want to. Okay, here. So when I ask you, not in the exam, this will not be in the exam, but in general, when I ask you, show that M is a manifold, okay? Some space, please show that it's a manifold, prove that it's a manifold. What do you need to provide? It means that I need to provide a collection phi and u, right? Or u and phi, that cover M. Correct? Any question about that? So this is the point. If I ask you, please show that this thing is a manifold, then I need to show that, okay, at every point, here is the function, the map, that maps this neighborhood to the real line, right? And vice versa, when I'm telling you, here is a manifold, and we're going to do analysis on it, given M as a manifold. This implies that you can consider, you can assume that there already exists a collection of neighborhoods and maps, we call it actually charts, that cover M. Okay? So when we go back to the example of the sphere, the circle, S1, which is every x and y in the S in the R2 such that x squared plus y squared is 1. Okay? This is S1. Here is my space, S1. Right? Show that S1 is a manifold. Prove that S1 is a manifold. This is one of the problems that we have as maybe first homework in geometry control course or differential geometry course. How do you do it? Well, we said you pick up on any point. Maybe let's start by this point. What do you think about this point? This V, I need to, please bear with me here for a minute, please. So here is the point. Pick any point. Locally around the point, I need to map all these neighborhoods to the real line. Okay? Actually, I will extend this a bit. I will take all this guy, and I'll tell you why later on. One possible mapping is that I will map this to, I'll just project it on the y-axis. This is the real line. So every point will be mapped, will be represented by xy coordinate. Okay? Any problem with that? So please bear with me. I'll leave this for you to write. We will move there afterwards, but this is important. So my U1, this is U1, okay, is what? Is every x and y on your manifold or potential manifold such that, well, I'm taking the x positive thing, right? Okay? And my phi1 should map this guy to, my phi1 should map u1 to the real line. Okay, what's your phi1 please? Well, I selected my phi1 that will take x and y, right? X and y, and gives you what? I will just project on the y-axis. The projection is always easy because you go from higher dimension to lower dimension. But the problem is that you have to show also that the inverse works, right? The inverse takes what? Very good. The inverse takes what? And should give you what? X and y on the circle. On the circle, correct? Well, so please give me the two coordinates on the circle. Well, the y is y. That's very easy. What about the x? Can you give me x on the circle?
1 squared is 1 minus y.
Square root of 1 minus y squared. Is it positive or negative square root?
Positive.
Positive, because we already selected that positive part. Okay? So yes, here is a map. It's very easy to construct a map to flatten out this part. Any question about that? Any question? The map has to be diffeomorphism, meaning it has to be differentiable all the way. So this is very easy to differentiate it with respect to x and y. Actually, there's no x dependence, and for the y, it's just 2y. It's linear, the best map ever. It's C infinity. It's even analytic. Over there, the y component is also linear. That's fine, but this is a bit difficult. Let's get its derivative just to make sure the things are correct. What is its derivative? It's negative y over the square root. Okay? This function is fine except at y equals what? Positive or negative 1. Right? This is why I excluded these 2 points. Okay? So I know the answer from the beginning. But if you start with everything, then you can remove later. Okay? So my function phi1 is very well defined, diffeomorphism on u1. I'm done with this part of the manifold. Please consider other parts to cover the whole manifold. Okay? Any question?
Does
Yes,
it have
sure.
to be the first derivative or like all derivatives?
All derivatives, but if you keep differentiating,
Right.
nothing will happen.
I was wondering if
All
you had, like,
derivatives, yes.
if you had like 3 halves or like y to 3 halves.